Hello everybody and welcome to week 6 of building scalable distributed systems. This week we're going to focus on the new database technologies which have emerged in the last decade or so. And these are typically known as NoSQL and new technologies. So a quick overview of what I'll talk about in this session is the realm of NoSQL databases, a quick aside on a technique called consistent hashing, which is useful for building scalable databases and extending them, and also a quick overview of NewSQL databases, and these will be then covered in more detail in the reading that accompanies this module. So NoSQL databases have emerged to try and overcome many of the difficulties that we've talked about with relational databases and making them scale horizontally on low-cost machines, essentially cloud infrastructures. So NoSQL databases typically get rid of a fixed schema. There's no fixed schema. You can store data together in various structures according to the problem. They have much simpler data models. We'll talk about the 4 that are listed there. They're designed to be horizontally partitioned and for data to be replicated to support high availability. Each of these products is typically proprietary and has its own database query language, and so this kind of introduces some impedance mismatch for portability. If you write your systems to one database, it's a lot harder to move it to another database because the query languages are totally different. And as we talked about in the last lecture, there are many implementations of these databases. It's a very complex technology. And each model, of course, in the general terms, not just specific implementations, each model has its own strengths and weaknesses. And you can see in the graph on the right there, this depicts the typical scalability you would expect from each model. Obviously, this does depend on the implementation because every implementation is different, but typically you would expect key value stores, as they're the simplest, to be the most easily scalable, followed by big table clones or column databases, as we'll call them in this session, followed by document databases, which start to introduce more complexity into the data model and the query languages. And then typically graph databases are still able to scale, but not to the extent that many of the other models typically do. But these are still very highly scalable technologies. So let's quickly look at these. KeyValue databases. A KeyValue database is essentially a simple hash table. You basically associate a key with an opaque data structure. To access the data, you just need to know the key. You hash the key to find the actual value's location and retrieve it or update it. So because of this essentially distributed hash table structure, they're extremely easy to scale because you can just distribute the nodes across the whole distributed infrastructure that you have and just find them very efficiently by looking at the key and its location. Typically, because these databases allow you to replicate information, you will find that it's possible to get conflicts on updates, the sorts of things we talked about with vector clocks. And each database will typically have some sort of versioning scheme, sometimes vector clock based, or maybe it's just last rider wins type techniques to enable you to handle conflict resolution on concurrent updates. They also typically use a technique called consistent hashing, which we'll talk about in a couple of minutes. A leading example of KeyValue databases is REAC, and there's just some information on REAC here, and if you do the reading and the exercises associated with this module, you'll get to play with REAC and understand the basics of its REST-based API. So let's take a quick look at hashing in distributed databases for distributing keys across different nodes. So here we have an example on the slide where we have 3 keys. We put them through a hash value, which is based on the number of nodes, a modulus of the number of nodes, in this case 4. So each key is hashed to one of the nodes in the system on the right. So of course, this works really well until you add nodes, or possibly remove nodes too. What's going to happen? Have a quick think if you can before you move on to the next slide. Well, what happens is that when we add nodes, the mod value changes. So we're now mod 5, not 4. And this causes the values of the keys to hash to different nodes. Therefore, when we add a new node, we're going to have to relocate all of these keys across different nodes. And in theory, we have to locate 1 over n objects will only remain in the same place, the rest will move. So we're moving, if we have 10 nodes, we're moving 9/10 of the objects to new nodes. Only 1/10 remain in the same place. Of course, this value gets worse as n grows. And this can cause cascading failures as the databases just get overwhelmed as we add new nodes. So many of the data objects need to be relocated to different databases that you can't do any useful work. Consistent hashing is a technique which has been developed to try and overcome this limitation of modulus-based hashing for distributed systems. The basic idea is that consistent hashing maps objects to the same database node as far as it possibly can. It means that when a node is added, it takes its share of the objects from all the other nodes. And when it's removed, the objects that the removed node hosts are then redistributed. Only those are redistributed to other nodes in the system. The main idea behind consistent hashing is to associate each node with one or more hash value intervals, where the interval boundaries are determined by calculating the hash of each cache identifier. As you can see in the diagram here, the hash space is conceptually organized as a ring. And each node, depicted by the different colors here, is allocated a partition of that ring's hash space. So when you hash a value for a key, you follow it to the ring and you allocate it to the node which manages that partition. The advantage of this is that if a node is removed, its interval is taken over by the node with the adjacent interval. So if suddenly the blue node was removed, then its objects would be allocated to one of the other two. And the others would all remain in place. And theoretically, this means that when you add and remove nodes, only 1 over n keys are invalidated. So 1/10 if there's 10 nodes are invalidated, rather than 9/10 if there are 10 nodes. So consistent hashing is a very effective technique that's deployed in several distributed databases to handle the scalability of the underlying horizontally scaled infrastructure. So back onto database types, column-oriented databases. The heritage is in the Google Bigtable technology, and they basically allow you to organize your data as columns, whereby each column is a key and each row is a set of a key and a set of column values, where columns are basically name value pairs. So on the right here you can see that we have a key is the type of wine from the Loire Valley in France, and it's described by 3 name value pairs, red, white and location. In the same database we have a key for wine from Washington, and this has the same key value pairs as columns, except it has a different one, a new one, climate, which describes the climate for Washington wines. So this hints at what you can do with column-oriented databases. Because there's no schema effectively, you can have different columns to suit the problem in each object. And there's no limit conceptually to the amount of columns that you can have for each key value. And so some may have 2 or 3 columns, some may have 20 columns. And they They provide a very useful structuring technique for many different types of problems. For example, if you want to analyze logs, logs are a classic example that uses column-oriented databases. Each log key row can be maybe a day, and then the column key can be the timestamp of the actual log entry, and then value is the actual log entry itself. And these are organized in a single row, which is essentially a really wide row. In most databases, this can be gigabytes wide. So column-oriented databases are very powerful and widely used in the big data space. The leading example of this is probably Cassandra. Again, in the reading, you'll get to explore some of its interesting features and its query language, and essentially it's introduced a fixed schema which makes it almost look like SQL. Interesting development in the technology directions there. Document databases really just store JSON objects, or sometimes XML, but typically JSON nowadays. So you can have a nested JSON structure, and you can allocate that a key in the database and store it directly. There's no enforced schema. You're basically describing your document using the JSON notation. And documents just have IDs, which are typically hashed across the distributed nodes that make up the database. MongoDB is probably the leader in this space, widely used, many applications, powerful master-slave based architecture for scalability and replication. And again, in the reading, you'll get to read about how Mongo works and potentially install and play with it. Finally, graph databases. These organize data as their name hints, a graph. This is a very natural description for many types of problems. Think of Facebook, where a person has friends, that person has friends. You can easily organize this data as a graph. There's different types of graphs, but typically you'll find that nodes have properties. They're connected to other nodes via links. These links may have properties as well, and links may be traversable either in one direction or both directions. So they are very suitable for certain types of problems. Leading example of this is Neo4j, which has a really powerful query language called Cypher. Again, in the reading, you'll get to read about Neo4j and install and play with it. In the last 5 years or so, there's been a pushback on NoSQL technologies, and people have tried to bring the benefits of SQL databases, such as a standardized query language, i.e. SQL, to distributed database technologies. And there's been many implementations of these. Some are pretty successful and widely used, but they typically have limitations. They don't fully implement the full SQL standard. A good example of this is VaultDB, originally based on the HStore project from Brown University. It enables you to describe your schema relationally and then distribute it across partitions in a cluster. It's designed to enable you to store, for each node in the cluster, to store its partition in main memory, hence making it fast. And there's ways you can back up each node's partition periodically to provide some measure of durability. But they provide also durability by replicating each partition, so if one fails, there are more than one others that can take over. There are limitations in how this works, though. Again, the full SQL language is not supported, it's only a subset. And the way each node works is that it is essentially single-threaded, so every query is submitted to the nodes in exactly the same order. This gets rid of the problems you have with conflicts where concurrent updates occur to different keys. When the updates are local to a particular partition, they're super fast. But when they try to do queries across multiple partitions. They have to be coordinated, and this can lead to coordination and slowness in the database. But again, a very widely used technology. I believe it was bought by IBM reasonably recently. And a really interesting case study to see how you can take the tenets of distributed databases and exploit them in a SQL model. So that's this module, and the next one we'll look at the database technologies, how they work, their features they have, their strengths and weaknesses, and hopefully you'll get a feel for this whole very complex technology space.